I think I literally have to wait for the green light before I start. I think it's not, or do you hear me? So I can also start like that. No. No. That doesn't work so far. Okay. Yeah, okay, fair enough. All right, now, so, well, first of all, thanks a lot for the invitation, so it's really a pleasure to be here. I'll talk about a joint project with Holger Dette, which is actually concerned both with locally stationary processes and, in a sense, also with change points, so I hope it fits well into the workshop program. All right, so let me first give you some motivation for what we are doing. Well, in a wide range of time series applications, the stochastic properties of the data change over time, and often it's more realistic to assume that the properties change gradually than abruptly. And moreover, in a number of applications, one may expect that the properties are more or less time invariant for a certain while before they then gradually start to vary. And actually, in such situations, people are often interested in the question, what is the time point where the properties start to vary? So let me first give you two examples to illustrate this. The first one concerns this simple time-varying mean model here, where mu is the time-varying mean, epsilon the residual, x are the observations. Yeah? And you may have the following situation in this model here. So it may be that the mean function is constant until a certain time point u0, and then it gradually starts to vary. Yeah? And the question in this situation is then how to estimate the time point u0. So this question occurs, for example, in the context of climate or temperature data. So what you see here are yearly global temperature anomalies from 1850 to today. And if you look at the data, then you see that, well, it appears that they are upward trending, yeah, so which is, well, today commonly known as global warming. And if you look a bit more closely, then you see that the upward trend is fairly strong in the second half of the sample, but, well, not so much in the first half or in the first third of the sample. So it appears that the mean of the temperature data is fairly stable for a certain while, and only then the warming trend kicks in. Yeah, and this is why people got interested in the question, what is the time point where the warming trend kicks in? So that's the first example, and the second one concerns volatility estimation. So here I've written down a very simple volatility model where sigma squared is the time-varying variance, epsilon the residual, and x are again the observations. And, well, if it comes to volatility modeling, what people are usually interested in is forecasting. So in this simple model, this means the following. What would presumably would do is you first get an estimator of sigma squared at the time point 1, and then, well, the simplest thing you can do is you just extrapolate constantly into the future, meaning that you just take your estimator of sigma squared at the time point 1, and then you use this directly as a volatility forecast, at least for the near future. Yeah? And so if you do that, well, you have to estimate sigma squared in a certain way, and if you don't want to put any parametric restrictions on sigma squared, well, you have to use a non-parametric estimator. So for example, what you could do is you could use a kernel estimator with a one-sided kernel, meaning that what you do is you localize around the time point 1 in the time direction with the help of this one-sided kernel. So you take data from a small neighborhood around 1, and then you use this data to calculate your estimator. Yeah? So that's, you know, one thing you could do in this simple model here if it comes to forecasting. Now, let me assume that we have the following situation. Let me assume that the sigma squared function, the time-varying volatility, is indeed not time-varying around the time point 1. Yeah? So it is constant for a certain while until the time point u0, and only prior to this time point, it starts to vary over time. Yeah? So in this situation, you may do the following. So if you knew the time point u0, you could just take all data from this time region here between u0 and 1 and calculate a very simple estimator of sigma squared at time point 1 from these data. So for example, you could just take the sample variance or something like that. Yeah? And you know, presumably this is a much better estimator of sigma squared at the time point 1 than a complicated non-parametric estimator that is based on a small amount of data from a neighborhood around the time point 1. Yeah? So in this situation here, then it would be very nice to know the time point u0, or at least to have a good estimator of it. Yeah? And, well, so this plot here is just meant to illustrate that this situation that I just explained to you may indeed occur in practice. So what you see here are S&P 500 daily returns, and if you look at the data, then, well, it appears that the volatility level here is fairly stable, and then you get to a point where it appears to go upwards and then it goes down again. Yeah, but that's just an illustration here. All right, now, so these are the two examples that I actually wanted to mention, and well, there are some other examples in the background, and I must say that I'm a bit of an econometrics person, so most of the examples that I have in mind come from economics and finance. Nevertheless, I would be very much interested in learning more about other potential applications from other areas. So if anyone knows a good application for this type of estimation problem, I would be very happy to talk to him or her about that. All right, anyway, so this is it for the illustration. So the next thing I want to do is I would like to introduce the model setting and the estimation problem in a rigorous way. So first of all, we assume that our observations come from a locally stationary process of variables x, which for simplicity, let's assume, is univariate. Now, you may ask, well, why a locally stationary process? Well, the situation that we have is we have a time series whose properties change smoothly over time, and that's nicely modeled by a locally stationary framework. Now, the next thing, so let lambda be some time-varying feature of the process. So let lambda, for example, be the mean, the pth moment, a vector of order covariances, or the whole time-varying distribution function. And, well, as before, what we do is we assume that the stochastic feature is time invariant on the rescale time interval from u0 to 1, but it varies smoothly prior to u0. Yeah? So the situation that we have in mind is indeed this situation here. The feature of interest is time invariant in this area here from u0 to 1, but it starts to smoothly vary prior to u0. Yeah? So I mean, clearly I could have also written down the model setting the other way around, meaning that I could have also assumed that the time-varying feature is constant between 0 and u0 and then starts to smoothly vary over time. But that's a matter of taste, so for the theory it doesn't matter which way you write it down. All right, and then, well, as before, we're interested in estimating the time point u0. That's the goal of the whole thing. And actually, we do not want to restrict attention to a very specific time-varying feature like the mean or something like that, but we would like to come up with an estimation procedure which allows to deal with a wide variety of stochastic features, including these examples here. So technically speaking, we are able to deal with any feature lambda which has this property here. And this property tells you that lambda is fully characterized by a set of moments that I've written down here, where script f here is a family of measurable functions. Yeah? So as a side remark, so clearly at the end of the day we are not able to deal with any family of measurable functions, but we have to make sure that the family is not too complex in the sense that, well, you have appropriate covering numbers, so appropriate bounds on the entropy numbers basically, yeah? But that just as a side remark. And, well, so that maybe looks a bit technical at first sight, so let me give you a few examples to make clear what is meant. So if lambda is, for example, the mean of the process, you can write this as the expectation of the identity function. So, well, the family of functions here is very simple. It just has one element, which is the identity. So the same if lambda is the pth moment. So then again, the family of functions only has one element, which is x to the power of p. So if you now look at the situation that lambda is the time-varying distribution function, things become a bit more complicated. But you can write the distribution function as the expectation of an indicator, and from this it's easily seen that the corresponding family here is a family of indicator functions. Yeah? All right. Now, so that's the model setting we're looking at, and the next question is how to estimate the time point u0 in this setup. So, well, our estimation procedure basically proceeds in two steps, and the first step is a sort of preliminary step, if you like. And in this step, we construct a so-called measure of time variation. Now, roughly speaking, a measure of time variation is a function which measures the amount of time variation in the feature lambda. So, strictly speaking, the definition runs as follows. We say that a function d that maps the unit interval to the positive reals is a measure of time variation if it has this property here. Yeah? And this tells you that the function d at a time point u is equal to 0 if the stochastic feature of interest is time invariant on the interval from u to 1, and it's strictly positive if there's some time variation going on in this stochastic feature. Yeah? And this property here immediately implies that you have the following. it holds that the function d is equal to 0 at all time points larger than u0, and it is strictly positive at all time points smaller than u0. Yeah, so this function then helps you to discriminate basically between intervals where there's no time variation going on and intervals where there's some time variation going on. Yeah. All right, so this is how we define this measure of time variation, and the next question is how to construct such a measure. Well, for the construction, let me first introduce some notation. So first of all, note that this moment here, so that's just a deterministic number, right? So this number depends on the function f, the time point little t, and the sample size big T. Okay, so I just use this notation here. Now, next, for simplicity, I assume that these moments can be written as functions mu f of rescale time. Okay, and this is actually a simplification because in the general case, this equality here only holds approximately. Okay, and well, then you have to think about what to do about the approximation error. However, I do not want to talk about these technical details here. So for simplicity of exposition, let me just assume that the equality is exact. Okay. So I can then write these moments as functions of rescale time. And well, as I said, by this property P, I know that lambda is fully characterized by this set of moments here, right? And well, this in turn means that time variation in the stochastic feature lambda is equivalent to time variation in at least one of these moments here. Or put differently, as these moments are functions of rescale time, I can also say the following. It holds that time variation in the stochastic feature lambda is equivalent to time variation in at least one of the functions mu f. Okay? Now, why am I telling you this? Well, if you put all these remarks together, what I basically tell you is the following. If you want to come up with a function which measures time variations in the stochastic feature lambda, you can equivalently try to write down a function which measures time variations in the functions mu f. Yeah? And this is what I'll do in what follows. Okay, and well, the idea is fairly simple. So first of all, note that if the function mu f is constant on the interval from u to 1, then we have the following. So here, this is basically an average of the function values of mu f, where I take into account time points from v to 1, okay? And clearly, if mu f is constant on this interval here, then this average here will be equal to the average where you take into account all time points from u to 1, yeah? Now, next, I write down this function here. So this is, well, that's the definition here, and as you can see, this is basically nothing else than the difference between these two averages here. So, and from what I just said, this means that, well, if indeed mu f is constant on the interval from u to 1, then this function here should be equal to 0 at all time points v which lie in this interval. Yeah? And from this, it's, well, now it's pretty easy to come up with a measure of time variation. So what you do is you just take this function, and then you take the supremum over all time points v in the interval from u to 1, and then you also take the supremum over all functions f. And this indeed gives you a function script d, which has the properties of a measure of time variation. Yeah? In particular, what you get is the following. If all the functions mu f are constant on the interval from u to 1, then this guy here will be equal to 0 for all time points v in this interval and for all functions f. So if you take the supremum over all f and over all time points v, you will still get something which is equal to 0. Yeah? Meaning that if there's no time variation on the interval from u to 1, then the function script d at the time point u will be equal to 0. And on the other hand, you can also show, but I do not go into detail here, that if there's some time variation in at least one of the functions mu f on the interval from u to 1, then you can show that script d at a time point u is positive. It's strictly positive. Yeah? So what we have here is indeed a measure of time variation. All right, now that's the construction. The next question is then, well, how to estimate this guy here. So that's not observed. That depends on some moments that I do not know. So and the estimation is, well, fairly simple. So first of all, note that this integral here, well, that can be approximated by some sort of Riemann sum, and then you just plug in the definition of mu f, and this tells you that this guy here is equal to an average of these moments, and this you can approximate by a sample average. Yeah. So what you do is, if you go back to the definition of the function d, you just replace these two integrals here in the definition by the sample averages, and this gives you this estimator here of the function d. And then as before, well, you just take this estimator, you apply the supremum operator here to the estimator, and this gives you then an estimator of the measure of time variation. Yeah? So that's the whole story here. Now, so this is it for this preliminary step, how to construct and estimate a measure of time variation. And in the next step, I want to use this measure of time variation to come up with an estimator of the time point u0. Okay, now, and so the idea of the estimation method is the following. So observe that by the definition of a measure of time variation, I know that this guy here, that the measure is equal to 0 at all time points larger than u0. Yeah? So if I rescale the measure of time variation with square root t, it will still be equal to 0. On the other hand, if when I look at time points smaller than u0, I know the measure there is strictly positive. So if I scale it up, it will explode at these time points. Yeah? Okay, and well, the same hopefully holds for the estimator or something similar. So indeed, what one can show is that if you scale up the estimator, then it will also behave in a stable way at time points larger than u0. So in particular, it will be big OP1 at least. And at time points smaller than u0, it will explode in probability. Okay? And the idea is now to exploit this dichotomous behavior of the statistic of this estimator. Now, this is done again in 2 steps. So the first step is a sort of transformation step. And well, the transformation, or well, first of all, what type of transformation do we do? So we want to transform the scaled estimator such that it behaves approximately like a function that has a jump at u0. Okay, and the transformation goes as follows. So you take the scaled statistic, then you pre-multiply it with rho t. So rho t is a sort of shrinking factor. So this is a null sequence of numbers which converge sufficiently slowly to 0. Yeah? And then you just apply some function phi to the whole thing. So phi is assumed to be strictly increasing, and it's assumed to be normalized to be 0 at 0 and 1 at infinity. Okay? And now if you go back to this formula here, so this tells you how the scaled statistic behaves for large sample sizes. If you keep this in mind here, then it's well fairly easy to see that the transformed statistic has this behavior here. Yeah? So in particular, then the transformed statistic converges in probability to 0 at time points larger than u0, and it converges to 1 at time points smaller than u0. Okay, so what you have here is then, this means that this transformed statistic behaves approximately like a step function with a jump at u0. Yeah? Okay, that's the first step, the transformation step. And maybe one quick remark on this here. So phi and rho t, these are the 2 tuning parameters of our framework. Yeah? And so I just wanted to mention here as a side remark that, well, indeed, these 2 guys are kind of harmless tuning parameters in a sense. So I cannot go into detail here, but if you would look at the asymptotic results that we have, then you will see fairly quickly that these asymptotic results tell you how to pick phi and rho t. So there's a sort of natural choice for these 2 tuning parameters. And in this sense, you know, you do not have the situation here that we throw in 2 tuning parameters in the method and we have no idea about what to do with them. But we kind of know, at least heuristically, fairly clearly what we have to do about them. So here you do not have something which is as problematic as a bandwidth parameter or something like that. Yeah, but that's just as a side remark. All right, so that's the first step, and then in the second step, I want to use this transformed statistic to construct a criterion function which is approximately minimized at u0, and well, this is the criterion function here, and this actually has a rather nice geometrical interpretation. So first of all, as I just said, this transformed statistic, little qt hat, behaves approximately like a step function with a jump at u0. So it looks a bit like this here, right? So like a smooth version of such a step function here. Now, the value of the criterion function at a time point u can be regarded as this gray shaded area here. Yeah? So if you first have a look at the small bit of the area, so the length is 1 minus u, the height is little qt hat at a time point u, so that's the second part of the criterion function, and this big part of the area, well, that's just u, so that's the first part of the criterion function. Yeah? And intuitively, well, I think it's pretty clear that this area should be minimized at a time point u which is small, which is close to u0. Because if you make the time point u fairly large, you will also make the area fairly large. If you make it fairly small, the area is also pretty large. So you know the minimizer should lie around u0 somewhere. Yeah? And this suggests an easy way to estimate the time point u0. What you do is you just take the criterion function and then you use the minimizer of the criterion function as your estimator. Yeah? And this is indeed what we do. So this is our estimator of the time point u0. Right. Now, so this is how we estimate the time point. Next, let me quickly try to make some connections to the literature. So, well, actually, well, as far as we know, there's no competing or no alternative method to estimate the time point u0 in the literature in our general framework. However, there are some competing or alternative methods for some special cases of the framework. So in particular, if you go back to this time-varying mean setting that I introduced in the introduction, then you could, for example, do the following. So at least under certain conditions, you can regard the time point u0 as a breakpoint in a higher order derivative of the mean function. Yeah? So if you knew the order of the derivative where the breakpoint is, then you could just use some change point methods to estimate this breakpoint. Yeah? So that's the first thing you can do. The next thing, clearly, you could try to use sequential testing methods, and this has, for example, been done by Mercurio and Spokojny in the context of this simple volatility model that I also discussed in the introduction. And if you again go back to the time-varying mean setting, then there's also a recent approach by Malik and co-authors, and they set up a sort of p-value based procedure. And actually, the third procedure here, this is the one which is closest to ours because it also works with some sort of transformation idea. Yeah. Okay. Now that's it in a nutshell for what is there in the literature, or for what we know is there in the literature. Let's put it like that. And so next, let me quickly say something about the asymptotic properties of the estimator. So first of all, well, I would like to at least give you a flavor of the assumptions that are needed for the theory. So I won't go into technical details here. I just, will roughly describe what are the assumptions. So first of all, well, clearly we want the process to be locally stationary, and we also need some mixing conditions on the process. Then thirdly, well, the model variables should at least have some moderate moment conditions. They should fulfill some moderate moment conditions. Then, as I already said, the family of functions f should not be too complex in the sense that you have appropriate bounds on the covering numbers. And then, lastly, we also put some assumption on the degree of smoothness of the measure of time variation. So first of all, note that, well, we assume that the underlying stochastic feature is varying in a gradual and smooth fashion. And this, in turn means from this it's clear that the measure of time variation will also be moving slowly, gradually, yeah. So it will be a smooth function at the end of the day. And here what we assume is that this measure of time variation has a certain degree of smoothness. In particular, it should be as smooth as a polynomial of order k around the time point u0, or technically speaking, we assume that this ratio here between the measure of time variation and this polynomial of order k converges to a positive number as u approaches u0 from below. Yeah? Okay. And actually, it turns out that this degree of smoothness k here is fairly important for our results, in particular when it comes to the convergence rates, which I think is intuitively clear because this degree of smoothness k, this reflects how smooth the feature lambda varies around the time point u0. And if you have something which varies very, very slowly, it's extremely hard to estimate the time point u0. Or put differently, this means that if you have a high degree of smoothness k, then your estimation problem becomes extremely hard. Yeah? And this shows up, or this is reflected in the convergence rate. In particular, what we get, as you will see in a minute, is that the higher k, the slower the rate will be. Yeah. Okay, and well, in particular, we get the following. We can show that the estimator converges to the true point u0 at the rate gamma t, and well, the rate gamma t I've written down here, and as you can see, it indeed depends on the degree of smoothness k. And it also depends on the shrinking factor rho t. And well, as this is the case, you may ask the question, how to pick the shrinking factor appropriately, such that gamma t gets as fast as possible. And well, the answer is that if you pick rho t at this rate here, then gamma t will have this rate here, meaning that if k is, for example, equal to 1, so if you have something, a measure of time variation which behaves linearly around the time point u0, then you will have in this case, a convergence rate of t to the power of -1/4, for example. Yeah. All right. Now, so that's it for the asymptotic result. So I don't know how much. 2 minutes. Okay. Okay. So then I skipped the simulation. So maybe just one remark on the simulation. So we did simulations for a lot of different model settings, including this time-varying mean setting, volatility models, AR models with time-varying coefficients, and so on. So for those of you who are interested, just have a look at our paper. Okay, but I'll skip it here. And I quickly go back to the two examples from the beginning. So the first example was the one on the temperature data, and there the question was, what is the time point where the warming trend kicks in. Yeah. So, and these are the temperature data, and the estimator of this time point is or our estimator of this time point is indicated by this dashed line here. And as you can see, I mean, if you look at the time series up to the dashed line, there doesn't appear to be too much trending behavior in there. So I guess at least the estimator should be in the right region. Yeah. And then the same for the volatility data. So there the question was, I'm starting at the time point 1 at the present time point, and then I want to go back to the time point where the volatility level starts to strongly vary over time. Yeah, and well, this is again the estimator of this time point, and again, I guess, well, that's, I mean, a fairly sensible estimator. So just by eyeballing, it appears that in this area here, the volatility level should strongly go up, whereas here, it appears to be, fairly flat. Yeah. Anyway, so, well, that is for the application. So let me quickly conclude. So what we've basically done is we've investigated the question how to estimate a smooth change point in a locally stationary setup. So this is basically what everything boils down to, if you want. And while we've derived some asymptotic properties, in particular the convergence rates of the estimator, and we also looked at the small sample performance, and well, for future work, two things would be kind of nice to have. So the first one is we only have the convergence rate so far. So would also be nice not only to have point estimates, but also confidence bands or something like that. So it would be nice to come up with a distribution result, but we are far from that, I would say. And the other thing is that our measure of time variation may also be used to construct tests for time invariance and stationarity, and this is also one thing we would like to have a look at the future. All right, so that's it. Thank you.
Time for a couple of questions. Ryan?
Mighty, two quick questions. It's appealing to try to maximize or minimize a statistic which is a soup of a whole family of functions, but in practice, what do you do? I mean, in particular, in with respect to the last thing, testing, isn't it true that if this family is too large, then basically you will always detect a breakpoint even if there is no one? And so what is really different with respect to the other methods which basically pick one F out of your capital F?
Yeah. Okay. I mean, this is true. So clearly, if you have an extremely large family of functions, then you will always detect something basically. Right. Yeah. So that's clear. So I mean, this means that you should kind of sort of regularize a bit, or in particular, if you have an application. So the best thing you can do is really to try to pick the smallest family of functions, which is kind of informative. Yeah. Right. So, I guess that's kind of something which is not a particular problem of this procedure here, but that's in general true. So you have to kind of, if you do some testing problem or something like that, you will have similar issues here.
But what is different if I just took a one-element family? Isn't that the same that other people did somehow?
Well, I mean, what are you thinking of, for example? So who?
Just the first moment to speak, or the second.
Yeah, I mean, then you won't get the procedure of which also has been, written down by someone else. But clearly, you will have alternative procedures. Or
so your procedure cannot be interpreted as a version of other procedures where actually F is just, say, linear or.
Well, I do, at least not to my knowledge. No.
Okay.
No.
Okay. And you have made comparisons there?
Well, not really. Not in terms of simulations. So just we simulated ours.
But there are not many papers who detect smooth changes. I mean, there's nothing to compare.
I mean that.
There's nothing to compare because there are no procedures which are able to detect.
No, but Spokane has this iterative.
Yeah, Spokane has more.
Yeah.
Right.
But there is also stationarity.
That's right.
Yeah.
Based on likelihood.
Yeah.
There is more work. I mean, what is important to understand is what is your local model behind. And for example, I mean, what you said is you can transfer it to a change point problem by looking at the derivatives. That's one way to look at it. But actually, a step before is that if you want to look at local changes, you actually need a local model. And what people, for example, did is, and then you go into the whole bunch of literature about bump hunting and mode hunting and so on. What they did is They looked at local variations from constant functions, like for example local linear variation, and then you can cook up even optimal procedures in order to detect that locally on all scales. And then you get multi-scale procedures in the independent case, not in these complicated time series contexts, of course. But then you get in a sense, procedures which get optimal detection rates and achieve optimal detection boundaries in order to get these local deviations.
Okay,
There is some
maybe we can talk
but it's
about
all
that.
it's all in the independent case.
Okay.
As far as I know.
Okay.
That's very informative.
My
Thank you.
question concerns, you see the last but one slide, that is the global warming situation. You see, I think that the estimator depends in the situation, what is your model behind it, what was now said, because it depends whether you assume that there is a just jump or there is a smooth this derivative set. It really depends, and you get different estimators as soon as you just work with. It really depends on the functions that you are taking into
Sure. I
account.
mean, if you would in this example here, well,
This
assume
is-
a jump or something like that. So probably we get it somewhere here or whatever, or 2 jumps. Yeah. Sure. I agree with you. Yeah.
Yeah, but there is a literature not for such a difficult setup, but for IID situations, for the gradual change, there is a number of papers on it. But this is IID errors behind it. There are papers.
Okay, I think we're going to have to pause the discussion on this for now, but maybe some of these aspects can be picked up at the coffee break later. But let's thank Michiel again. Thank you.
Thank you.